Hi, I'm Marco Santamroggio, and I do really hope all is great with you. Today, I'm going to guide you into the Santa's world. More precisely, with this presentation, I will guide you into the essay part of the Santa's world. The system architecture journey will start with a specific focus on FPGA-based system design and on how to go from there to autonomic heterogeneous computing systems. Technology progress induces paradigm shifts in computing. The invention of the programmable microprocessor in 1974 has resulted in the evolution from the pure hardware-based computing to the software-based computing. Today, we are also entering a new era, an era in which computing systems are no longer seen as monolithic, high-performing, power-hungry, single-core systems, but computing systems are getting smaller. We are observing systems composed by more than one core, systems in which the underlying computing infrastructure is embedding both big and little cores, and maybe even more than one for each category. System in which heterogeneity is the key. Specialized core is trending up. Instead of just one big, let's say, super pumped core, which is not really a technical term, but it can help us in getting the idea, we're preferring several smaller, dedicated cores. Such a scenario will provide us more efficient architecture where computation is going to be executed on the most efficient element. This is also obviously introducing new issues to take care of. But we are scientists. We are expecting to face these issues because they are representing new challenges that are just waiting for us to be solved. And I need to change the slide. Oh, there we go. In 21st century, due to Moore's law, the number of gates that can be squeezed into a tiny chip area has increased such an extent that a full hardware-software system can be implemented on a single chip. With the advent of what has been called the system-on-chip, SoC, the design of electronic consumer products has started on an era of digital convergence, leading to the integration of numerous applications onto a single device. The mobile phone is a typical example of such a technology integration. All this power comes at a cost, and it has led to a high power consumption, high density cost, large form factor, low mean time between failure, low reliability, increased security risk, and a lot of side effects and conflicts. Many of these issues can be resolved if some sort of adaptation is introduced in the system. To properly manage all these resources, we are interested in having, as we just said, a system able to adapt itself after the chip has been fabbed. As an example, to deal with faults, to try to take advantage of the reconfiguration of the system to recover from damages. Being too hot or too cold can impact the way in which our mobile is running out of battery. Having a system capable to adapt the underlying computing infrastructure to implement the same functionality in a different way can provide us a better energy saving. This obviously may come to a cost. Maybe this new implementation is not going to perform as well as the previous one. But if the only other solution was not to have a working device, well, I think it can be a reasonable cost to be paid. Finally, but the list can be longer, and I don't want to spoil future discoveries that we are going to have maybe through meetings. We may be interested in having a system able to adapt its behavior because of the surrounding environment in which it is used. According to the surrounding condition, a system may be interested in behaving in different ways. Nowadays, we are used to drive cars that are enriching our driving experience with a lot of information gathered by the car itself, without even thinking about autonomous driving cars. We may have information about the pedestrians, and this is definitely an important information. Now, as depicted in this figure, driving the car to work at 6:30 a.m. is definitely characterized by different scenarios from the one that we may have by driving at 8 a.m., just right in the middle of the rush hour, as shown in these other pictures. Because of this, our pedestrians identification system may behave differently. One thing is being able to detect just few sporadic pedestrians who may also be moving slowly because of the time. Remember, we were speaking of a 6:30 a.m. scenario. And on the other one is being able to detect the pedestrian, at 8 a.m. when they are moving like crazy because they are getting late to go to work. And because of this, they are rapidly changing also the way in which they are moving. The amount of data that has to be processed is different, but the response time is not. The latency in being able to collect information and providing useful feedbacks to the driver is not changing because of the context is getting more complex, because the context is getting more complex. And the system has to be able to adapt its behavior to deal with it, not the other way around. And finally, I finally reached the final slide. That's one of the areas I'm working in. Reconfigurable computing is breaking down the barrier between hardware and software design technologies. Given the architecture and the design flexibility, reconfigurable computing has characterized this progress in hardware-software co-design technology and in a vast number of application areas such as scientific computing, biological computing, artificial intelligence, signal processing, security, control-oriented design. This is just to name a few. It has been a great pleasure to describe you this research area. If you're interested in exploring more of this fantastic world of autonomous heterogeneous computing system, well, you know how to contact me. Just drop me an email and I'll be more than happy to get in touch with you. Talk to you soon, at least I hope.